Okay, so welcome everyone. Our speaker today is Athanasios Sourmelidis from Graz University of Technology, and he will talk about on the interface of universal zeta functions and frequently hypercyclic vectors of translation operators. So Athanasios, welcome, you can start.
Thank you, Dimitri, and thank you for the introduction. And I would like to thank the organizers for inviting me to give a talk in this seminar. And I think it's a great thing that what you're doing, organizing this and giving the opportunity for all of us to also present our work here. So I am an analytic number theorist, and my main field of research is on the value distribution of zeta functions, which is an object from analytic number theory. And these functions have some property which is also connected with linear dynamics. And I want to show you these properties and also any possible connections that they will have with these translation operators, as I say. So I will start with a classical theorem from complex analysis. Probably everybody have seen it once or two or twice in courses in complex analysis. It's Merkelian's theorem. You have a compact set in the complex plane without holes, so with a connected complement, and you have a function f, which is continuous on the compact set k and analytic in its interior. Then for every epsilon, you can find a polynomial that is close to your function f over the set k. Of course, the graph doesn't really just the property really, because the polynomial is also close to f at every point of the set k, not just the same image, but fair enough. So Merkelian's theorem basically says that the polynomials, the set of polynomials, is dense in the Banach space of functions which are defined on this compact set K that are continuous and analytic in its interior. And when this Banach space, this is a Banach space with a norm of the maximum norm of the compact set K. And this is a stronger result than Runge's theorem, which was a predecessor of Merkelian's theorem. And it says that the polynomials are dense in the smaller space of holomorphic functions with a sequence of semi-norms, which of course induces the topology of uniform convergence on compact sets. So this is a stronger result. And basically, if you change the error and you want to have a smaller error, then you have to choose a different polynomial. That's what Merkelian theorem says. If you change your function f and you keep the compact set k, you have to choose a different polynomial. The Merkelian theorem produces a different polynomial. And if you change also the set k, the same happens again with the polynomial. So the question is, I mean, the theorem is ineffective. So it says there exists a polynomial, but it doesn't give an explicit form for the polynomial. So we don't know how it looks like. So the question is, could at least these polynomials, even though we don't know how they are, can be generated by only one function? So you have one function, then you induce on it, you perform it some natural operations, and then you get a polynomial or something close to this polynomial. And this question has been answered before in the 1920 by Birkhoff. So Birkhoff proved that if you take the space of holomorphic functions to the entire functions, and you define the translation operator t with index alpha, which takes a function f to its the same function but shifted its argument by alpha, then there is an entire function whose orbit under the action of the operator, here t with index alpha n is just the composition of the operator n times, and you act over the G, you have a set generated of functions in the space of entire functions, and this set is dense in the space of holomorphic functions. And this is a discrete thing because you just have n integers and then you take iterations. But there is also the continuous version, which is, of course, also simpler to prove. And you have a one parameter family of operators with index alpha tau. Tau is a real number, positive real number. And you define this parameter, one parameter family to the same space, and you send the function to alpha tau, the same function shifted by alpha tau. Then you can still show that this new orbit, as it is defined here, it's still dense from the space of holomorphic functions of HC. Of course, this follows from the above, but I want to keep the continuous analog in Bay because we will need it later. Now, this was in the 1920s, but Mergelian's theorem was later, so you can also use it to these two theorems to produce some other results. Basically, if you have a domain, an open set of the complex plane without holes, and you define the functions that are holomorphic in this open set, then this is again a Banach space or a Fréchet space, to be honest, and you can still show that that there is such a function inside the space whose orbit, the continuous orbit or the discrete orbit, is dense in the space. And using Mergelian's theorem, you can even reduce it to the space of continuous functions on a compact set K with connected complement, which are also analytic in its interior. So you have such a set K1, you have some function F1, and then there is a shift of your function G, which is close to this F1. Then you take another function, let's say F2, from the same set K1, and then you can find a shift of the same function, a different shift now, which is close to F2. So you can really keep one function and then its orbit can be close to anything you want, basically. And that's why, I mean, this comes from operator theory or from functional analysis. This particular function G, wherever it lives, whether it's an entire function or it's an analytic in a set omega, or it's a continuous analytic in a compact set K, it's called a hypercyclic vector because these are also topological vector spaces. And Birkhoff actually proved that the set of hypercyclic vectors in whichever space you are, it's dense itself. It's not just that each of them has a dense orbit, but also the set of hypercyclic vectors is dense and it's big. It's a G delta set. And the proof, Birkhoff's proof, is based on Bayes' category theorem, which of course gives this strong result, but also it's exactly because Bayes' category theorem is also ineffective, meaning you don't know how this G looks like. There is a G, or actually there are many Gs that do the job, but you don't know how they look like. So I took the liberty to paraphrase the opening from the Asterix and Obelix comic strips. And you say that it's 1975 after Christ, and the space of entire functions is entirely occupied by unknown hypercyclic vectors. You know there are there, but you know how they look like. Well, not entirely. One small class of indomitable functions still holds out against ignorance inside a small vertical strip on the complex plane. It's right here. And we will zoom in there and see what happens. So Voronin, Sergei Voronin, 1975, proved a version of Mergelian's theorem, or Birkhoff's theorem, if you prefer, which states that if you have a compact set K with connected complement without holes, but this set now lives in the vertical strip of complex numbers with real part between 1/2 and 1, and you take a function f which is continuous on K and analytic in its interior, but it's also zero-free, it doesn't have zeros, then there is a real number such that the shifted Riemann zeta function on the set K is epsilon close to your function f. So basically, you have the operation over the zeta function by the vertical translation I tau, and this is close to f. So basically, the orbit of the Riemann zeta function under this action of operators is dense in the space of HK, the continuous functions on K, which are analytic in its interior. And now the Riemann zeta function is a very well-known object. And I will spend the next minutes or slides, at least for those who are not accustomed with the Riemann zeta function, to introduce it anew. So first of all, it should be called the Euler-Riemann zeta function because it has two expressions. It can be written as an infinite Dirichlet series and also as an infinite Euler product. Now, it's called Dirichlet series because it's in honor of Dirichlet, who also worked on this series. And it's not exactly a Taylor series, right? In the Taylor series, the argument is an infinite polynomial. Here, you just have that the argument is in the exponent All right. And in contrast to Taylor series, which have a disk of convergence, the Dirichlet series have half planes of convergence. So they converge on the right half plane when the real part of the complex number is 1, for example. In this case, it's 1. So this Dirichlet series is absolutely convergent in this half plane, and it also has an Euler product representation, which is this product over primes. And it's also absolutely convergent. And in analytic number theory, at least, I mean, I know it's not very usual, but for the complex numbers, we denote them by S and not Z or Z. So why Euler? So Euler was the first to take the fact that we know that every integer is uniquely decomposed as a product of prime powers. And he showed that if we take the argument x of this function of this Euler product to be greater than 1, which is an absolutely convergent Euler product, then each term can be, it's a limit of a geometric series, right? And because we have absolute convergence, everything, you can interchange everything, and you can multiply the products together, and then you can reconstruct all integers, all positive integers, at least once. And that's how he proved the identity when x is a real number, not a complex number. He was considering only real numbers. So he could show this identity between Euler product and Dirichlet series. And he used this identity to prove once more that there are infinitely many primes. How he did that? Well, by contradiction. He said if there were only finitely many, this product would also be finite, right? It would be a finite number. But this is also the limit of this expression, which we just showed that it should be equal to this Dirichlet series. But this Dirichlet series, when the argument x goes close to 1, converges to the harmonic sum, which diverges, right? A contradiction. Therefore, there should be infinitely many primes. Now, why would Euler need to prove this? He already knew that. We already knew it from Euclid that there are infinitely many primes. But Euler was the first to open the gates to an analytic proof of the infinitude of primes. Actually, even Dirichlet, 100 years later, based on this idea, he could prove that there are infinitely many primes in arithmetic progressions, with a stronger result. And again, after Dirichlet, Riemann came in 1859, and he considered the zeta function as a function of a complex variable now, not just real. Now, Riemann was a geometer, as I think we all know, Riemannian geometry or Riemannian metrics. But for his habilitation, to defend his habilitation, he wrote an article in number theory, his only article in number theory. And, well, the remaining is history. So first, he wanted to study the Riemann zeta-function as the function as a function of a complex variable. And he could prove that it has a holomorphic continuation to the whole complex plane, except of a simple pole at s equal to 1, which you expect because it's the harmonic sum, diverges. And he also proved that the Riemann zeta-function has a sort of functional equation. So on the one hand, you have zeta of s, and on the other hand, you have zeta of 1 minus s. So there is some symmetry around the vertical line of complex numbers with a real part 1/2. And you multiply with something which is well known or well described. See, this is just an exponential function. This is factors of the gamma function. So he proved this. And lastly, from this formula, you can easily see what are the zeros of the Riemann zeta-function on the right of on the half plane of complex numbers with real part greater than 1, because there you have an Euler product, and it's an Euler product, it's an infinite product, it doesn't have zeros. And also on the left of 0, because of the functional equation. And there are zeros on the left of 0, on the negative integers, which occur from the poles of gamma s½ in the functional equation. So if we have the sketch here, we can see that here it's in this half. Oh, I went too far. Let me see. Yes. So here it should be 0, free, no zeros. Here there are the zeros in the negative integers, -2, -4, -6, and so on. The Riemann zeta-function has a pole here, and all other zeros should lie in this blue strip. Let's call it blue strip. So if there is a 0 here, then by the functional equation, there should be also a 0 here, because S is mapped to 1 minus S. Also, the Riemann zeta-function has a certain reflection principle, which has a connection of numbers on the upper half plane and the lower half plane. So if it had a 0 here, it would also have a 0 here. By the functional equation, it would also have a 0 here. So it suffices basically to just study the Riemann zeta-function on the right half plane, on the right of 1/2. Or even to the upper half plane, because everything else is described by the functional equation and the reflection principle. And Riemann could not prove anything about the zeros in this strip. He didn't know how to do it, and he made the following conjectures. So if NT denotes the number of non-real zeros of the Riemann zeta-function inside the strip, but also in a smaller rectangle, the sides of the rectangles are from t to minus t and from 0 to 1, then this should be equal approximately t log t over pi. And this has been proved a few years later by von Mangold in 1895. He also predicted, because he could see that if we take pi of x to be the prime counting function, which counts primes up to some threshold, some magnitude x, then if someone could prove that the Riemann zeta-function is 0 free on the vertical line of complex numbers with real part 1, then this would imply the prime number theorem. Well, then it was still known as prime number conjecture, but after a few years, Hadamard and Lavallee-Poussin proved independently, following Riemann's path or way, that actually the Riemann zeta-function is 0 free, and thus the prime number theorem is true, mainly that this limit exists and is equal to 1. And the last conjecture he made was that if it should be that all these non-zero complex zeros, they're not just arbitrarily somewhere inside this purple strip in this blue strip that I showed you, but exactly on this red line right here, on this red line that passes from 1/2. So, and this is not proved, of course. It's almost 165 years and so on. It's the Riemann hypothesis. And Riemann did these conjectures, and then he moved on with his life. He moved on with his research. I don't know whether he was more interested in other stuff or he had certain insight that this could be a very difficult problem. But the mathematical community was really interested on this connection between zeros and primes, because this would give information on how the primes are distributed among the integers. So it was already predicted by Gauss in 1791 that the prime counting function should be approximately x over log x. This symbol here just means that the limit of the refraction goes to 1. And it was already known before Riemann that if someone could prove that the Chebyshev function, which is this sum here, is asymptotically equal to x, then this would imply the prime number theorem. Here, the sum is over the so-called lambda function or von Mangold function, which is given as the logarithms of primes when n is a prime power and 0 otherwise. And one would say, why should we have a weighted prime counting function like the von Mangold, this lambda, capital lambda n? Because it has a connection with the Riemann zeta-function in this form. The logarithmic derivative of the Riemann zeta-function is given as a Dirichlet series, again, where the coefficients are this function. And now we have a function of a complex variable, we have logarithmic derivative, we have zeros and poles. So this, I mean, it just gives you the answer straightly. You use the residue theorem, right? So by the residue theorem, you have that this Chebyshev function can be written as this vertical integral right over here, plus some error. This is called the Perron formula, but it's really basically an application of the residue theorem. And then what you do is use the residue theorem to move this vertical line to the left. Now, when you go to the left, you have to consider what happens here, here, and here. And Riemann couldn't know this. He needed some more theory, which has been given later by Hadamard in his thesis. And this is just a big error, which is we can control it. But while you move this curve in this rectangle to the left, you cross the pole of the Riemann zeta-function at 1, and that gives you this main term here, as well as the zeros that lie inside this strip. And this gives you this sum here. So if someone could actually show that this sum is small, then you have the prime number theorem, because this would be basically the main term. And basically you would have that the subseteq function is x plus some error function, which is given by some logarithm which is not important, but also times the maximum of x to some power of the real part of zeros up to some threshold. But if beta cannot be 1, then the main term is x, and then you have the prime number theorem. Actually, if you even bound the beta as close as you get to 1/2, if you could bound it that close, you get the optimal error term from the prime number theorem. Because then you would have x plus something that is bounded by square root x. And this has been proved that it's the best you can get. Well, however, there are zero-free regions for the Riemann zeta-function, but none as good as what the Riemann hypothesis predicts, or even a weak Riemann hypothesis. The best you can get is a zero-free region is the white area, and you can see that as we go higher, this goes asymptotically to 1 and to 0. I mean, for sure there are no zeros at 1 and that in the vertical lines 1 and 0, but we don't know whether there are strips on the left of 1 that are zero-free. This would give a major improvement on the error terms of the prime number theorem. So mathematicians really tried a lot to improve on these zero-free regions. There is an exhaustive literature about this, and I will not discuss it here, but one concept that they thought about, okay, we cannot prove zero-free regions. How many zeros are off the critical line? Like zero density estimates, can there be many? And already in the 1910s, Bohr and Landau showed that if we want to count the zeros which are off the critical line, the vertical line 1/2 plus IR is called the critical line for obvious reasons. If you take the set of zeros which are off the critical line with real part greater than sigma 0 and of height t or minus t, so in a certain open box, then there are not too many. There are a small power of t as t goes to infinity. And as I told you before, von Mangold proved that the zeros are equal to t log t. So this means that at least the zeros cluster around the critical line 1/2, while when you're away from the critical line, there are not too many. We will use this identity, this inequality later, that there are not too many zeros. And here I have bolded Bohr, because that's not Niels Bohr. This is Harald Bohr. He was the brother of Niels Bohr. He was a mathematician. And Bohr had the following idea to tackle the Riemann hypothesis. So he observed that the general Dirichlet series, here we don't have n to the s, we have e to the lambda n to the times s, which is a more general case. It can be written, is actually a Fourier series, right? You have some sum of some positive, some coefficients times some frequencies. So if we take the special case where the frequencies are 2 pi n over q for some fixed number integer q, then this represents the Fourier series of a periodic function. All right. So what is the general case? What if lambda n is not 2 pi n over q, but something like log n? He had in mind the Riemann zeta-function. Does this function also behaves periodically or almost periodically? And that's how he invented the uniformly almost periodic functions. So basically, a function from R to R is called uniformly almost periodic if for every error, epsilon, you can find a length L, which depends on epsilon, such that in every interval of the real line of length at least L, there is a period such that the function f behaves periodically. Almost periodically, right? This is not 0, but it's epsilon. So for every epsilon, you can find such a translation number or period tau. And not just you can find one, you can find them frequently. In every interval of length L, there is at least one such translation number. And Borg continued this investigation. He proved actually that any such function can be represented as a Dirichlet series in that way. And this is not equality. It's the same principle as a Fourier series for a periodic function. If it converges, then it's equal to f or at its points of continuity. If it not, then it just represents a Fourier series. And then he extended this to the complex plane. So he took a function f on a vertical strip of complex numbers with real part a and b, and he said that he considered it to be analytic, and he said that it should be uniformly almost periodic, but using the same definition now as before. There is a length L such that in every interval of length L you can find a period such that this supremum holds for every complex number. And again, he showed that such a function has a Dirichlet series representation. Now, and his first train of thought, maybe I was not there to see that, but he probably thought that any Dirichlet series which is absolutely convergent in some half plane, it is an analytic uniformly almost periodic function. And the Riemann zeta-function is such an example of an absolutely convergent Dirichlet series in the half plane sigma greater than 1. So it should also be uniform. So it's definitely analytic almost uniformly almost periodic. And then his question is, could we show that the Riemann zeta-function has also this property to the left of 1, inside the strip 1/2 1? Because if we could really show this property for the Riemann zeta-function, then the Riemann hypothesis would hold. And the proof is by contradiction. It's only 3 lines or something. You assume that there is a 0 off the line. It's somewhere between 1/2 1. And then you take a small disk around this hypothetical 0, so small that it is inside this vertical strip of complex numbers. Therefore, this inequality makes sense. This maximum is less than the supremum. And because we assume that the Riemann zeta-function is uniformly periodic, for every epsilon, which we will choose later, there is a period, there's a sequence of periods, tau m, such that this supremum is less than epsilon. Also, so the maximum of this disk should also be less than epsilon. And we choose the epsilon in that way, which is equal or less, doesn't matter, to the minimum of the Riemann zeta-function on the boundary of this disk, which we chose in such a way that there is no 0 of the Riemann zeta-function on this disk. So this makes sense. So you can do it for a sequence of periods, tau m, or translation numbers. And then you just apply Rousses's theorem, right? So from this inequality, you deduce that the shifted Riemann zeta-function has also a 0 in this disk, or equivalently, that the Riemann zeta-function has a 0 at its disk, shifted by tau m, not only in the first, but going higher and higher. And not just in some disks, but frequently, because these periods are appearing in a frequency of 1 over lambda. Therefore, the number of zeros, of hypothetical zeros of the critical line, which are greater than 1/2, with real part greater than 1/2 plus epsilon, is greater than the number of zeros that are inside disks, which are inside this open rectangle. And this is at least T over L, because of this inequality. But in the 1910s, Bohr and Landau showed that this thing is definitely not of size T, but of something much smaller. Thus, a contradiction. Thus, there are no zeros. End of discussion. So what's the problem with this proof, right? We assume that zeta is analytic uniformly almost periodic, and Bohr quickly realized that this is not possible, because an analytic uniformly almost periodic function is bounded in the vertical strip that it's defined, and the Riemann zeta-function is not bounded in this strip. So the argument breaks down. However, his ideas led him and his collaborators to study the value distribution for other values, not 0. So 0 is a bit elusive, or a lot elusive, for the Riemann zeta-function, but apparently for any other complex number, which is not 0, is visited infinitely often and in high frequencies from the Riemann function. So in the beginning, he showed that if you are just on the right of one, you can actually prove a Picard theorem, that the Riemann function takes any non-zero value infinitely often. So only the zero is not taken. This we know because it has an Euler product. Then he moved to the left of one, and he studied the image of a vertical line, sigma plus it, under the Riemann function, where sigma is fixed between 1/2 and 1. And he showed that it's dense in the complex plane. So you have a vertical line, you map it, and then this is like a spiral, but still it will cover the whole complex plane after some time. And the last result is a more advanced one. So you take a complex number which is not zero, and then you count the number of A points, as they called, which are the solutions of the equation zeta of S equal to A, inside this rectangle of sides sigma of edges sigma 1 plus n minus it and sigma 2 plus n minus it. And then he showed with a yes and actually that this limit exists and is a positive real number. So not only the Riemann function takes a value, but it takes it frequently. And this depends also on the sigma 1 and sigma 2. So I would like to show you, to illustrate at least the proof of the second result, because this is the predecessor of Voronin's theorem. This is about approximating complex numbers, while Voronin's theorem is approximating complex valued functions, analytic functions. And basically the proofs are more or less, the ideas are the same, although here they are more simple, while in Voronin's proofs they are more involved. So how to do it? You take, if you remember, the Riemann function has an infinite Euler product. So you consider the finite Euler products, or they are called truncated Euler products. This is basically the first, this is a product of the first m factors of the Euler product of the Riemann function. And you also take a similar function, which is also associated with a vector of real numbers. So instead of having sigma plus it, you have sigma and a vector of real numbers, which twist your factors. And Bohr proved first that if you take a complex number which is not zero, then for any sufficiently large integer m, there is a vector of real numbers in the unit cube of dimension m, such that the logarithm of this truncated Euler product, which is of course minus the sum, just basic calculations, minus the sum of the logarithms, and then you take the Taylor expansion of this thing, and you basically have that this behaves like this, is close to the logarithm of A. Now, this is a bit technical to the proof, but the intuition is the following. It's Riemann's rearrangement theorem for the real line, which the Riemann rearrangement theorem says that if you have an infinite series, which is conditionally convergent, so it's convergent but not absolutely convergent, then you can rearrange its terms such that they are dense in the real line, right? You can approximate every real number. This is the analog in the complex plane, right? You can see that this series when you send m to infinity, this series is conditionally convergent because you have twists, and these twists are in the unit circle, which forces this series to converge. But when you take the absolute values, you just have 1 over p to the sigma, and this diverges. That's how you get this denseness. All right, so we approximate a number like this with these functions here, and then we need to approximate the logarithm of this function on the given vector theta 0 by the original truncated Euler product. We use a continuity argument. We have our solution, which is close to logarithm a, sorry. And then you take a box around this vector of real numbers such that any other solution theta, which is inside the box, will give you that this function is close to logarithm a. Now, if you choose a real number tau such that the fractional parts of this vector is inside this box, you have, inside this box, then the logarithm of the truncated Euler product should be close to the logarithm of this twisted Euler product. Let me remind you that this logarithm, this zeta m of sigma plus I tau, is basically the first term here. So this is close to the logarithm of this one, and this is close to logarithm of A. So we don't need just one tau, we need many of them, because for a certain reason. So we use Weyls' approximation theorem, which says that if you have a vector of real numbers, which are linearly dependent over the rationals, this means that any linear combination of them, non-zero linear combination of them, is also non-zero. Then the multidimensional curve, here it's a multidimensional curve, you take the fractional parts, visits every box of the unit cube proportionally to its volume. So exactly what this exactly what the statement says here, that this limit exists, and it should be the number of taus which corresponds to this group being inside the box is the volume of the box. Using this fact, then we can show that since the logarithm of the primes are irrational numbers and linearly dependent over the rationals, and this follows from the unique prime factorization of the integers, the measure of those real numbers tau in this interval, such that the truncated Euler product is close to A, is positive. This limit exists, and it's a positive number. It's a positive number which is also independent of how long you take the truncated Euler product. It doesn't depend, but we need that we take sufficiently large n's. So we have this now, and now we need to involve the Riemann zeta-function. Now the problem is that these truncated Euler products do not approximate the Riemann zeta-function in the conventional sense, when the real part of a complex number is between 1/2 and 1, because it's not absolutely convergent, not even uniformly convergent, this representation when we are in this strip. However, Bohr proved that there is an L2 approximation. Basically, this lim sup exists. Here you have the mean square of the Riemann zeta-function approximated by a truncated Euler product, and this is smaller and smaller as the longer you take the Euler product. And Bohr used this fact basically to show that the number of real numbers tau in the interval 0t, such that the Riemann zeta-function is close to a long Euler product, is at least 1 minus c/2. C is from the previous step. Then you just use the second step, and you show that the number of tau divided by in the interval 0t divided by t, such that zeta of sigma plus A tau is close to A, is at least c/2. So not only you prove the denseness, not only you prove that the curve is dense in the complex plane, but you also give a positive proportion of real numbers tau which are close, which make the Riemann zeta-function close to A. So this is also a predecessor of the third result of Bohr. So basically, we proved that this is positive. We didn't show that the limit exists, we just showed that it's positive. And to show the equality, it needs much more involved techniques. So that is the proof for complex numbers, and the proof for complex valued functions like Voronin is, as I said, analogous. So Voronin, first of all, proved a multidimensional version of Bohr's result. He fixed a complex number with real part sigma between 1/2 1, and then he take the multidimensional curve of the zeta function and its derivatives, and he showed that it's dense in Cn plus 1. And the proof follows the same steps. In the first step, he proves this denseness, and in the second step, he approximates with some truncated Euler products. In the third step, he uses this L2 approximation. And you can already see that this is like a predecessor of the universality theorem, of Voronin's theorem, because if we know that this multidimensional curve is dense, and you want to approximate a function, you just take a Taylor series of the function, you throw the tail, some tail up to some n, then you have finitely many terms, which it's a polynomial approximation of your function, and then you approximate with the Riemann zeta-function the Taylor coefficients of this polynomial, and thus you can get also a weak version of Voronin's theorem. However, Voronin proved the stronger thing, so he needed the first step, but not for complex numbers, but for complex valued functions. So he needed a proof for function spaces. And this is basically what followed after in 1973 by another Russian mathematician. I think Voronin actually asked him whether this is possible, whether he could get the first step, that the logarithms of these truncated twisted Euler products are dense in the space of continuous functions in the compact set K, which are analytic also in its interior. And this other Russian mathematician, which I cannot pronounce his name right now, proved this, and then Voronin could actually implement this step and the second and the third step to get his theorem. And I think I was a bit fast, but I would like to continue the next Monday with discussing more about Voronin's theorem, which I could have the opportunity maybe to show it again. It was here. So it's again, this is a statement. You have a zero-free function and you approximate it. And this is a wide class of functions, right? Except of the ones that have zeros, you can approximate anything else. That's why it's called also universality theorem. And the zeta function is called universal. And this was done in 1975, and this sparked the interest of mathematicians, which after a few years, they started discussing what is so special about the Riemann function that could actually give you this universality theorem. Can we adjust it to get this theorem in some other strip, maybe, for other functions that have or that are of number theoretic interest? And even really afterwards, after 5 more or so years, there have been many results that prove that there is a zoo of universal zeta functions, and I would like to give you some examples next time, as well as what are the implications of Voronin's universality theorem for the Riemann zeta function, as well as for these other zeta functions, because the results are analogous. Lastly, there are types of universality. This is the simplest I showed you, but there is also joint, disjoint, hybrid, discrete universality, and I will focus mainly in discrete universality. And lastly, there is a connection between discrete universality and continuous universality, which is also implemented in the theory of these translation operators that I showed you in the first slide, and is also connected to linear dynamics. So I would like to thank you for your attention.